The rapid rise of high-speed drone swarms presents a significant threat to airspace security. These swarms, often flying at low altitudes and high velocities, are difficult to track using traditional detection systems. Their coordinated behavior and agility make timely identification and classification increasingly challenging, demanding more advanced surveillance solutions. AI perception of drone swarms using 77 GHz FMCW radar for counter-UAS security. A final-year project presented by the Department of Electronic and Telecommunication Engineering, proudly sponsored by Deep Silicon. Let's begin with our measurement setup. We collected radar data from a variety of drones, including custom-built quadcopters, commercial UAVs, and toy drones. The recordings were taken under multiple flight conditions to ensure a diverse and comprehensive dataset. This helped us simulate a wide range of drone behaviors, both isolated and coordinated. We use a millimeter wave cascaded AWR1243 radar board for radar implementation, with data acquisition handled through the millimeter wave digital signal processing board. We configured the millimeter wave cascade radar system using Texas Instruments Millimeter Wave Studio software. After experimenting with different chirp and profile parameters, we finalized a configuration suitable for drone detection. Using Lua scripts, we programmed both the radar and signal processing boards and began capturing raw radar frames. These frames were then transferred to our laptop for processing. As shown here, we used several types of drones for data collection. Using the collected data, we created a drone radar dataset. It consists of data from 125 single drone capture sessions and 15 drone swarm sessions, covering a variety of motion patterns and interactions. To create the drone swarm dataset, we applied data augmentation techniques for the collected data. This included modifying range, velocity, and angle of arrival values to simulate synthetic swarm conditions. For range shifting, we applied a phase shift along the ADC sample's dimension. For velocity shifting, the phase shift was applied along the chirp's dimension. Additionally, for angle shifting, we applied a phase shift along the radar channel's dimension. For all signal processing tasks, we use MATLAB software. These are the results of range shifting, velocity shifting, and angle shifting. After applying range, velocity, and angle shifts, we combined individual drone data to simulate drone swarm scenarios. As shown in these range Doppler maps, the swarms are accurately represented with multiple distinct drone signatures. We generated over 1,000 augmented time domain samples of drone swarms, each saved as a 256x128x16x12 dimensional data matrix in CSV format, with the 4 dimensions representing ADC samples, chirps, receive antennas, and transmit antennas. To estimate the parameters of the drone swarm, we apply 2D fast Fourier transform to the radar data to extract range and velocity information. For estimating the angle of arrival of drones, we apply angle FFT across the virtual antenna arrays. As shown here, the range Doppler map accurately displays the range and velocity of the drones, while the range azimuth heat map clearly visualizes their directions of arrival. To estimate the drone count, we use a simple blob detection algorithm. As shown here, it accurately identifies the number of drones. To identify drone types, we use a machine learning approach. First, we perform time frequency analysis of the drone radar signals using wavelet transform to generate scalogram images. Here we can see 2 scalograms for both single drone and multi-drone cases. Using these scalogram images, we created a radar dataset that includes both single drone and drone swarm scenarios. For the stationary drone cases, data was collected using 5 different drone types, while 3 drone types were used for the flying drone cases. The single drone dataset consists of 45,000 stationary drone scalogram images and 1,000 flying drone scalogram images. The drone swarm dataset consists of 60,000 stationary and 15,000 flying drone scalogram images. For our machine learning approach, we used scalograms as input to the model. We faced challenges when using only moving data due to limited viewpoint diversity in the training dataset. Motion artifacts also degraded classification performance. When we captured data in stationary mode, we were able to cover almost all angles. Therefore, we propose a soft mixture of experts approach, where two experts are trained separately on stationary and moving data. We selected the YOLO V11 architecture, considering both accuracy and processing time requirements. To apply our mixture of experts approach, we modified the detection head of the model. The experts are pre-trained on stationary and moving data respectively. In the first phase of training, we froze the experts. A gate mechanism followed by softmax outputs weightage for each expert for each image, and the sum of these outputs is used for final classification. We kept the detector and other parts of the architecture unchanged. We introduced a simplified architecture for the experts to maintain compatibility with our FPS requirements. These are some prediction results for multi-drone scenarios. Here, the confusion matrix for the moving test dataset is shown. The left figure displays output from our mixture of experts approach where both stationary and moving experts are used. The right side shows output from the model using only the moving branch. The results clearly demonstrate that our method outperforms the single expert approach. These metrics also show that the mixture of experts method performs better, although the FPS is comparatively higher. Let's do a quick demo. First, we'll select a CSV file that contains time domain radar data of drone swarms. Once the file is loaded, the processing will start automatically. After that, you'll see the results. The range velocity maps and range azimuth maps. These results are shown in 3 consecutive time frames. If you want a closer look, there is a button to zoom in and view detailed range velocity and range azimuth maps. In this example, 3 drones are flying in a specific area. A simple block detection algorithm has been used to highlight them, and you can even identify the types of drones present. All of this happens inside this easy-to-use software application.